So this is the first video for Principles of Analysis video course. And for this course, I'm going to be pretty much going off of Walter Rudin's Principles of Analysis. This is the standard book in at most universities for learning analysis. You may have taken a course in analysis on the real line or introduction to analysis before this one, but maybe not. So that's the main book I'm going to be referencing. I'm going to be mentioning it a lot in videos to come. Over here, I have another book mentioned, or just uh, pretty much I'm just showing this other book that I really won't be referencing much at all. But I've heard that a lot of students use this as well, as it says, a lifesaver. It pretty much, I don't want to say dumbs things down, but gives a lot more examples and uh, I guess puts things in simpler terms than this other book by Walter Rudin, which a lot of students, if it's your first time learning analysis, and reading this book by Walter Rudin may be a bit hard. He is a bit clever in his writing, but it's a great book, which is why I will be going off of that book. With that said, the first section is ordered sets and fields. So let's begin. First things first, if talking about like preliminaries in this first chapter, ordered sets and fields, maybe you've seen this in another class before. And well, we have the rational numbers, right? The set of rational numbers. And I'm going to be making a point in this slide, trying to get to a big point. But maybe you've seen that there is no rational number, p, such that p squared is equal to 2. There's no rational number p such that that condition's met. P squared is equal to 2. And we can, I guess, construct a sequence from first term being 1 and then 1.4, 1.41, so on and so forth. That tends to square root of 2, but I mean, we never really know what square root of 2 even means if we're just talking about rational numbers. And there's a theorem to actually prove this, which states that the equation p squared is equal to 2 is not satisfied by any rational p. Now here, because it is the first video, notice how I'm using a blue, not navy blue, but a darker blue, not a baby blue, for theorems. So I always use this color box for theorems, and I'll be mentioning other colors, like green's going to be for definitions, but we'll get there when we get there. But yeah, so for now, theorems are in that blue. And again, this theorem says that there is no rational, the equation p squared equals 2 is not satisfied by any rational p. So we're going to prove that, and proofs are in baby blue, as you can see here. So we're going to go ahead and prove this. So we're going to start by supposing there is such p. So because p is a rational, we can write m over n, where they are both integers and they are not both even. Otherwise, we can reduce it. So that's our assumption. So p squared, if we square p, well, this implies that m squared is equal to 2n squared. Right, just doing some little algebra there. And what does this imply? Well, here we have 2 times an integer. What is that? Well, that's just saying that m squared is even. Hence, m is even. So that means that m is divisible by 4. Right, because if m squared is even, m is even, so it's divisible by 4. And now it follows that 2n squared is divisible by 4 as well, right? Because m squared was divisible, m was divisible by 4. So n squared is even, which implies that n is also even, which leads us to our contradiction. Right, so therefore there is no p, or therefore our theorem is true. Now that we reached that contradiction. Okay, so Next thing is another theorem that says we're going to let A be the set of all positive rationals such that p squared is less than 2. And we're going to let B be the same thing, but now p squared is greater than 2. And we're going to say A contains no largest number and B contains no smallest. Right? We can't get to p squared equals 2. And this one I'm not going to prove because I'm trying to get to this point. I'm going to try to get to the point that rational number system, the system of rational numbers, has certain gaps. Okay, so the proof, I'm not going to prove this one again because I'm just trying to get to this point. The point that the rational system has certain gaps. So we need to deal with something else. So to get to that other rational system, to get to that other system that we can use, we're going to present some definitions first. So here you see a green box. That's because that's a definition, and the definition you can see here is going to be underlined and highlighted in green. So here we're defining order. So we're going to let S be a set. And an order on S is a relation denoted by this sign, which is less than, with the following properties. If X is in S and Y is in S, then one and only one of the statements is true. And either X is less than Y, either X is equal to Y, or X is greater than Y. Second condition is the transitivity. So if X, Y, and Z are in S, and if X is less than Y and Y is less than Z, then X is less than Z. Okay, next we're going to define what an ordered set is. And an ordered set is just a set S in which an order is defined. And order, order just means this up here. Okay, we're going to define, maybe you've seen this before, we're going to define what an upper bound is. Or if some of a set is bounded above. So suppose S is an ordered set and E is a subset of S. If there exists a beta in S such that X is less than or equal to that beta for every X in E, then we say that E is bounded above. Right? And we call beta that upper bound. There can be more than one upper bound. And lower bounds, I should have highlighted this. I'm going to underline it. Lower bounds are defined the same way. Just as it says here in the parentheses, with this symbol inequality in place of this one. Okay, so now we define the least upper bound, because beta, well, it is an upper bound, but there can be many upper bounds. So for this next definition, we're going to suppose S is an ordered set. And we're going to let E be a subset of S and say that E is bounded above. That means beta exists at least one. So suppose there exists an alpha. Now we're calling it alpha in S with the following properties. Alpha is an upper bound of E. And if there's such elements gamma that's less than alpha, then gamma is not an upper bound of E. So if these two conditions are met, or properties, then A is called the least upper bound. Right? Out of all the upper bounds, alpha is the least upper bound. Another word for that is the supremum of E. So we usually will just write A is the supremum of E, or A equals sup E. Greatest lower bound, or another word for that is infimum, is defined similarly. So if we have a set E, which is bounded below, Then the statement alpha is equal to the infimum E means that alpha is a lower bound of E, and that no beta with beta greater than alpha is a lower bound of E. And this might be a bit difficult to understand, so I'm going to include a picture. An illustration might help us here. So here we have an open interval at the top. Here we have open interval. And here we have a supremum. Why is it supremum? And when it's closed, why is it a maximum? Well, the maximum is the biggest element of the set. Right? But in this case, it's open. So that point, the supremum, doesn't necessarily belong to the interval. But it is an upper bound. It is an upper bound. And so are these points over here that are labeled upper bounds. But this point, the supremum, I'm going to circle it in blue, is the least upper bound. Right? Similarly with the infimum, it's the greatest lower bound because we have all these lower bounds over here. But infimum is the greatest lower bound. In this case over here, we have minimum and maximum, different from supremum and infimum. And then, well, we also have the lower bounds and upper bounds because, like I said, we can have more than one upper bound and more than one lower bound. Okay, so we move on to definitions, as this is pretty much just a preliminary lesson. So an ordered set S is said to have the least upper bound property if the following is true. If E is a subset of S, E is not empty, and E is bounded above, then the supremum E exists in S. This is a really important property, the least upper bound property. So if you want to pause a bit and kind of read it over, I guess not over and over again, but kind of digest it, go ahead. And we're going to go ahead and present some theorem here. Suppose S is an ordered set with the least upper bound property, with the property defined above, and B is a subset of S where B is not empty, and B is bounded below, just as our definition above tells us. And we're going to let L be the set of all lower bounds of B. Then alpha is a supremum of L, which does exist in S, and alpha is an infimum of B. In particular, infimum of B exists in S. So to prove this, I'm going to draw a real line to kind of help us. We're not doing analysis on the real line, but a real line can help us just to illustrate it. So first, since B is bounded below, L is not empty, right? There's at least one lower bound, which L here is a set of all lower bounds. So there's at least one, meaning L is not empty. So I'm going to draw a picture of what kind of maybe what you're thinking this looks like. So B is, we'll say this is a set B, right? I'm going to label it B. And L, I'm going to put in purple. L, we have this. These are all what? Set. These are all elements, or these are all lower bounds of B, right? Okay. So next, since L consists of exactly those Y and S which satisfy the inequality, Y is less than X, so all these points Y are less than points X for all X in B. We see that all of these points in here in B, I'm just going to put a bunch of points, those are all upper bounds of this set of lower bounds over here. I guess, of this point, this point, this point, and that point. Oh, and this point. Right, so all elements of B are upper bounds of the elements of A, of the set L. Okay, so we can conclude, or we can say that L is bounded above. Now, by definition of S and our hypothesis, we can say that L has a supremum in S. Call it alpha. So alpha, I guess I'll put it green, is the supremum of L. And here with the picture, you can see that this is going to be the supremum here. It's the one at the top, or not the top, but the greatest. I should say the least upper bound, right? So that's a supremum, alpha. And if gamma is less than alpha, then by definition of supremum gamma, by definition, the supremum gamma is not an upper bound of L, right? So if gamma was, say, here, because it's less than alpha, that is not an upper bound, because alpha is already the least upper bound, right? And you can see here that this element of L, this one here, is greater than gamma. So it follows that alpha is less than x for every x in B. And we can see that here, right? Let me erase gamma real fast. We can see that here, that alpha is less than all these elements in B. Therefore, alpha is an element of L, right? It's in the set of all lower bounds of B. And if alpha is less than beta, then beta cannot be an L, right? Since alpha is an upper bound of L. So that's just saying beta can't be on this side. Or if it is, then it can't be an element of L. Okay? So we have shown that alpha is in L, right? It's right here. And beta is not in L if beta is greater than alpha. So in other words, alpha is a lower bound of B, but beta is not if beta is greater than alpha. So by definition, what does that mean? That means that A, or alpha, sorry, is also the infimum of B, which proves our theorem. Okay, we move on to a definition. Maybe you've seen we define this definition a lot in our algebra courses, so linear algebra, abstract algebra. We define what a field is. So a field is a set with two operations called addition and multiplication, which satisfied the field axioms. In this case, we're going to label them A, M, and D. And I don't know what you're thinking. A field should be something like this, right? Is that what we're defining? No, that's not what we're defining here in this case. So a field is, first of all, we're going to satisfy the field axioms of addition, or A, axioms of addition. First one is if x is in F and y is in F, then their sum is also in F, so it's closed under addition. Addition is commutative. X plus y is equal to y plus x for all the elements in the field. Addition is also associative. As you can see, it's described here. I'm not going to go over them just to not to take up time. These are just axioms. And F contains, the field contains an element 0, such that 0 plus x is just x for all x in F. We also have that to every x in F, there's another element. In this case, a lot of people just call it negative x, such that if you add both of them, you get 0, or this element up here. So there's the axioms for addition. Now there's the axioms of multiplication. So if x and y both belong to F, then their product is also in F, so it's closed under addition. Multiplication. It's also commutative for all x and y in F. It is also associative. F contains an element. In this case, it's not 0, it's 1, such that 1 times x is equal to x for every x in F. And there's also that inverse element. So for every x in F, there's also an inverse, 1 over x in F, such that you multiply both of them and you get this element up here, the multiplicative identity. And finally, our last property is a law, which we call the distributive law. That's why the D. And this law holds for all x, y, and z in the field. And just a little notation. This shouldn't even have to be mentioned, but we'll do it. You should know this from maybe even high school. For x minus y, we write this here instead of x plus negative y, right? So on and so forth. We don't want to write this out, so we write x over y. Or especially like x cubed and 3x, we don't want to write x times x times x or x plus x plus x. Right, so that's just a little notation or just a remark. And then we go to propositions. So these are little things that, little theorems, I suppose, that we can prove. The axioms for addition imply the following. So A, if x plus y is equal to x plus z, then y is equal to z. If x plus y is equal to x, then y must be equal to 0. C, if x plus y is equal to 0, then y is equal to negative x. And D, the negative of a negative element is a positive element, x. I shouldn't use negative and positive so loosely here, but I'm just using it to maybe how you're used to reading things. But these things can be proven. A, B, C, and D. A is actually called the cancellation law. But I'm not going to prove all of them. I'm going to prove A. And you can go ahead and prove the other ones. But I'm just going to kind of show you how this works. So if x plus y is equal to x plus z, I'm going to use the axioms of addition, right? So we get y is equal to 0 plus y, right? And 0 is the same thing as negative x plus x, right? Two elements that add where their sum is equal to 0. And then what law or what property? I'm going to use the associative property to kind of group the x and the y. And then because we're assuming that x plus y is equal to x plus z, I'm going to replace x plus y with x plus z over here. And then I'm going to use the associative property again to group the negative x and the x. And what is our sum equal to? Well, just 0. And 0 plus z is equal to z, right? By the axioms of addition. Therefore, y is equal to z. And using axioms like that, you can go ahead and prove the other ones. Shouldn't be too difficult. Right now, we mentioned the other theorems or the other propositions, and to prove these, we use the axioms of multiplication. So the axioms of multiplication imply the following. First, that if x is equal to 0 and x times y is equal to x times z, then y is equal to z. So similar to the other propositions, but now with multiplication. We have b that says if x times y is equal to x, then y must equal 1. C, if x is not 0 and x times y is equal to 1, then y must be 1 over x. And finally, if x is not 0, then 1 over x is equal to x. Again, I'm not going to leave you in the dark. We will prove some right now. But we also have these these propositions. And the field axioms imply the following statements. So 0 times x is equal to 0 for every x in f. If x isn't 0 and y isn't 0, then their product is not 0. Here we take out, you can think of it as taking out the negative and then sending it to the y. So negative x times y is the same thing as x times negative y. And finally, negative x times negative y is equal to x times y. So here comes the proof for b. So for this one right here, why isn't this pen? There it is. For this one right here, assume x and y are not equal to 0, but that x times y is equal to 0. Right, so we're going to get a contradiction here. Well, then we get that 1 is equal to 1 over y times 1 over x times y. Right, and because x times y is equal to 0, well, this here is equal to 0. And anything times 0 is 0. Well, wait a minute, 1 can't be equal to 0, which is our contradiction. Therefore, b holds. Okay, now we're going to define what an ordered field is. So an ordered field is a field F, which is also an ordered set, such that x plus y being less than x plus z implies that y is less than z for all x, y, z, and f. And also, if the product xy is greater than 0, where x and y are both in the field, are elements of the field, this happens if x is greater than 0 and y is greater than 0. So those are the two properties that make up an ordered field. And then again, we have more propositions, more little theorems. And again, this is all preliminary stuff. Maybe you haven't seen it in detail though. So these are true in any ordered field. If x is greater than 0, then negative x is less than 0. Vice versa as well. If x is greater than 0 and y is less than z, then xy is less than xz. The product is less than that other product. If x is less than 0 and y is less than z, then xy is greater than xz. So similar to the one above, just flipping some signs. We also have that if x is not equal to 0, then x squared is positive. They have this right here, but if it's confusing you, you can just ignore this. And finally, if x is greater than 0 but less than y, then 1 over x is greater than 1 over y, and they are both positive. Okay, now to prove, now I'm going to prove 2 of them to not leave you in the dark, and you can do the rest as exercises. So first, A, if x is greater than 0, well then 0 is equal to negative x plus 0 by our axioms, which is greater than negative x plus 0. And why is this? Well, because x is greater than 0, right, from up here. So that's why this is greater than this over here. So negative x is less than 0. And that is if x is, we're just proving the other case. So if x is less than 0, then we can write a similar inequality, negative x plus 0, which is equal to x, is less than negative x plus 0. Why? Again, because x is less than 0, so then this here becomes less than this. So negative x is greater than 0 if x is less than 0. And now proving b, we're assuming that z is greater than y, so that's why we have, since z is greater than y, we have that z minus y is greater than y minus y, which, I mean, y minus y is just 0. Therefore, multiplying x times this here, the positive number, is positive, right? Because up here, if you look at b, x is also, we're assuming x is greater than 0. So this product should be greater than 0. And therefore, x times z is equal to x times z minus y plus xy, if you want to distribute that so you can see that, which is greater than 0 plus xy, which is equal to xy. So xz is indeed greater than xy, which proves b.